So today we're going to be doing the chapter 2 CQDs in chem. So which element has a similar chemical reactivity to nitrogen, carbon, oxygen, phosphorus or sulfur, and why? Now, out of these options, let's first identify what groups is everything in. Carbon is in group 4, oxygen is in group 6, phosphorus is in group 5, and sulfur is in group 6. Now, nitrogen, it's in group 5. So, when we say about chemical reactivity, we need to know that elements of the same group have the same chemical activity, or reactivity, my bad. But why? It's because they have the same number of valence electrons. This number of valence electrons lets it either share, give, or take, or whatever with other atoms from different groups the same way. So since nitrogen is in group 5 and phosphorus is also in group 5, it is phosphorus, P, because they both belong to the same group and they have the same number of valence electrons. Now, in which block of the periodic table is manganese? Now, we first need to take a small look. Let me draw here a periodic table. I know, very bad. Anyways, now we need to know that this block is the S block, this block is the P block. The transition metals are all in the D block, and these two rows at the bottom, they all belong to the F block. So manganese is a transition metal that's right here, Mn. So Mn belongs to the D block. Now, moving on. Predict the position of X in the periodic table, knowing that this is its electronic configuration. Now, we know that the position of X has to be in the third row because it ends at the third energy level. So it is in period 3. Now we need to count its valence electrons. You're going to say, oh, it has 5. Wrong. You need to count every single valence electron in 3. So if it ends at period 3, you need to count all the electrons in 3. 2 plus 5 is 7. Period 3, group 7. Now there's a new thing. When you're saying group 7, you need to say A, 7A. Or you could just call it group 17. Both are the same exact thing. Now, our teacher told us that for AP students use group 7A and for AS students use group 17. That's how they prefer to call it. Now, what's the factors that affects the atomic radius? The factors are 3. I'm gonna put like 3 arrows to explain. 1, 2, 3. The first one is the shielding effect. The shielding effect is the effect of the extra energy levels. So wait, I'll explain it now. So when you have the nucleus, these shells, the energy levels, they are making a shield for the nucleus. So the number of energy levels, the more energy levels you have, the higher the shielding effect you have. So that's shielding effect. And the number of quantum energy levels, so the quantum energy levels are the same as the energy levels. It's how many energy levels you have. And how many N do you have. And last but not least, the nuclear charge. The nuclear charge is basically the charge of the nucleus. Nuclear charge. Which means that it's the number of protons you have. So let's say you had element number 14, silicon. Silicon has 14 protons, so its nuclear charge is plus 14 because neutrons in the nucleus do not have a charge. So the protons are the only thing in the nucleus that are charged. So the nuclear charge is the charge of the nucleus, which is also equal to the number of protons. Now explain why the atomic radius of fluorine is smaller than nitrogen. Now, we know that, like if you look at your periodic table, fluorine and nitrogen are in the same group. Like here's nitrogen, then comes oxygen, then comes fluorine. They're in the same, period. Now we're not talking about O. They're asking why fluorine is smaller than nitrogen. Now, they have the same number of core electrons because they are in the same period. So, their valence electrons experience the same shielding because the difference is just in the valence shell, how many electrons is on it, but they have the same number of valence shells because they're in the same row. So exact same shielding and exact same number of core electrons. So fluorine though has more protons because fluorine is number 9 and nitrogen is number 7. Since fluorine has more protons, it has a higher nuclear charge. So the greater the nuclear charge of fluorine, the greater the nuclear charge of any atom actually, the more it pulls the electrons it has closer to its nucleus. So if fluorine has a higher nuclear charge, it can pull the electrons it has strongly or stronger, making it smaller, making it like closer, everything's closer to each other. So they're more like held together, you know? So that's why nitrogen is bigger than, what's it called? Like, first of all, you have to look at these. The shielding effect is the same in both of them. The number of quantum energy or the number of the energy level, the same. The nuclear charge is the only difference. So we start explaining about the nuclear charge. Now, why is the atomic radius of magnesium smaller than that of calcium? Now, magnesium and calcium are in the same group. Magnesium is right above calcium. So here's the periodic table, magnesium, then calcium. So why is magnesium smaller than that of calcium? Let's see. Do they have the same shielding effect? No, they don't. Magnesium is in period 3, so P3, and this one's in P4. So they're both in group 2. But calcium has 4 valence shells and magnesium is 3. So since the valence electrons of calcium are farther away from the nucleus, they have greater shielding effect. So they are less attracted to the nucleus, making calcium larger. So whenever you have a higher shielding effect, you're most likely going to have more energy levels. So here, and also to add, calcium also has a higher nuclear charge. So the shielding effect and the number of quantum energy are more important. So the shielding effect of calcium is greater than the shielding effect of magnesium because it has more energy levels. And since they have more energy levels, there's more shielding from the nucleus. So the nucleus can attract the valence electrons less. That's making the size bigger for calcium. Magnesium making it smaller. And we need to also know the trends down like in a periodic table. When you're going this way in the period and when you're going down a group, size increases. Size of the radius or atomic radius, actually let's call it AR. AR increases. When you're going from left to right, from right to left and up to down, the atomic radius increases. Now, question 7. Which of the following graphs represents the trend of atomic radius down a group? What did we say? When you're going down a group, atomic radius increases. So, it cannot be figure 1 and it cannot be it cannot be this, and it cannot be this. It has to be, listen, you're gonna say, why is it not this one? This one's increasing, then decreasing, then increasing, then decreasing. No, it's wrong. It has to stably increase as you're going down a group. It doesn't increase, then decrease, and increase, and decrease. It's stable, steady. So this is the correct one. How does the atomic radius change across a period and down a group? We just said, across a period from left to right, it decreases because the nuclear charge increases for the same shielding effect. When we have the same shielding effect, we talk about nuclear charge. Since the nuclear charge is stronger, when you go from left to right, it gets stronger. So it's attracting it more, making it smaller. And down a group, you have more energy levels. So you have more shielding, making the nucleus less able to attract valence electrons, making the atom itself bigger. Now, how does the ionic radius of an ion compare to the atomic radius of its atom? Now, here in this question, it's a trick question because it depends. If you have a positively charged ion or a cation, the cation, how does a cation form? It's formed when it loses an electron. So it has more positive charges. So now let's say you have 4 plus positive charges and only 3 minus negative charges. These 4 plus can pull in these 3 minus way more. Way more. So it's overpowered. So it's gonna get smaller than it's supposed to be. In the ion, when they're balanced, like 4 plus 4 minus, it's average size. It's the normal size. But let's say we have another element where it's 3 plus and 4 minuses because this is an anion because it has more negative charges than positive charges. Then you have less positive charges to pull in the negative ones. So you're gonna have to, the positive charges can't deal with all these negative charges, so they're gonna lose control of them and let them go, making the anion bigger. So the atom of an element is bigger than the cation, but the anion is always bigger than the atom. So if it's positively charged, because it's formed when it loses its valence electrons, the electrons in the valence shell are closer to the nucleus. This means they experience less shielding and they're attracted to the nucleus more, and their cations are smaller than their atoms. Whereas in the negative charged ion, when it gains electrons, that's when it's formed, it increases the electron repulsions. You have to also mention electron repulsions. Since you have more electron repulsions, they move even further apart. So it increases the size of the anion. I'm reading, I'll first explain them in my own words, then read the mark scheme answers in case I didn't mention something in the mark scheme. Now, moving on to the next question. Why does the radius decrease from Na plus to Si4 plus? Now, Na plus has 10 electrons because it's 11 and plus means minus 1. Si4 plus, Si is 14, so it also has 10 electrons. What do we call two elements or two atoms or ions with the same charge, with the same number of electrons? We call them isoelectronic. So these two elements are these two ions are isoelectronic. So the nuclear charge, increases from Na to Si4. So there's an increased reaction where it's between the nucleus and the outermost electrons. So it decreases the atomic radii. So yeah, that's the radius decreases from Na to Si4 because Si4 has a higher nuclear charge, so it is smaller, the radius, even though they have the same number of electrons. Now, trace on the same graph the sketch of an atomic radius strand corresponding to the given ions. So this is the ionic radius of the ions. Now they want you to draw the same thing, but they want you to draw it of the atoms. So the atomic radius of all these cations, the atomic radius is gonna be bigger than or longer than this, and for the cations it's gonna be less than this. So it's most likely just gonna be like there. I'm just gonna copy what they drew, and like they drew something like this, you know. They don't really care if you draw it correctly or not. They just want to see that you know that the ionic radius increases when it's an atom for the cations and decreases when it's for the anions. Now let's move on to question 9. Which of the following consider the two chemical species Se and Se2-. Write the electronic configuration of each. Now we need to first look at our periodic table. On the periodic table, Se is what's it called? Where is Se? Se has 34 protons. So Se is gonna be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p, I said 34, yeah, 4p4. That's for selenium. And for Se2-, it's gonna be the exact same, but 4p6. Okay? Now write the electronic configuration. We did that. Explain why the radius of selenium is larger than the radius of the Se atom. Now, the radius of selenium, they both have the same nuclear charge, of course, because they're the same species. But like I said, selenium has extra electrons. Since it has extra electrons, the protons cannot account or take control of these extra electrons. And there's gonna be more electron repulsions because now you have 6 valence electrons, where before you had 4 valence electrons. Or now you have I'm talking about last shell. There in the last shell now you have more than last time. So there's gonna be more electron repulsions. So they're gonna get further away, making the radius of the Se2- bigger. Mark's scheme says the nuclear charge is the same for both species, but the 8 valence electrons in the selenide ion experiences a greater amount of electron repulsion than the 6 valence electrons in the selenium atom. So these extra repulsions increase the average distance between the valence electrons in the ion, so the electron cloud around the ion is greater than in radius. Now, here it's telling you Se2- is isoelectronic with the Kr atom. From which species is it easier to remove an atom? And explain why. Now, first of all, we need to always write down electronic configurations. Now, for selenium or selenide, we wrote it. Now, let's draw it for krypton, which is gonna be where? Oh yeah, it's number 36. And krypton, by the way, is what's it called? It's noble gas. They're isoelectronic. Oh wait, don't have to write down the electronic configuration because they told you it's isoelectronic. Since they're isoelectronic, they have the exact same electronic configuration. But why is it easier to take from selenide actually than krypton? Now it's easier because both electrons are going to be removed from the 4p electrons. But the selenide's nuclear charge is plus 34, where krypton is plus 36. Since it has a higher nuclear charge, it's gonna attract its electrons stronger than selenium is. So we said that atoms are gonna attract more than they're gonna attract their own electrons more than anions. So anytime it's easier to take ions or take electrons from an anion than it is a stable a stable atom. Anyways, arrange the following in increasing size. First of all, we need to make sure they're all isoelectronic. Now, when you write out all the electronic configurations, or just look at your periodic table and find out how many. Actually, I'm gonna find out. So, Te is selenium, but where is it? Te. Oh yeah, it's number 52. 52 2 minus is basically 54. I minus is gonna be also 54. Cs plus is also gonna have 54 electrons. Ba2 plus 54, and La3 plus is also gonna be 54. So they are all isoelectronic. Now we need to look at their charges. Always, the most positive cation, or the cation with the most positive charge, is the smallest, which in this case is La3 plus, because it has 3 extra protons pulling in the electrons. Then it's gonna be Ba2 plus. Then it's gonna be Cs plus. Then it's gonna be I minus. Then Te2 minus. Why? Because the more, now we're going, so when you want to order them, it goes from greatest to least in the cations, but least to greatest in the anions. So this would be your order. Now we reach section 2.3. So write the equations to illustrate the first and second ionization energy of sodium. So first of all, ionization energy is the energy required to remove, it's the energy required to remove an electron from an atom in its gaseous state. 1 mole of an atom in its gaseous state. So the first is gonna be Na in its gaseous state, most importantly, which is gonna give you Na plus in its gaseous state plus 1 electron. And that's the first. Now the second is gonna be Na plus in its gaseous state, taken away from, it becomes Na2 plus. You're gonna say Na can't be 2 plus, it's fine. In this case, you're gonna forget everything you've learned before, plus another electron. And that's the first and second ionization energy. The second ionization energy of an atom is always larger than the first. Now, when you're removing, yes, it is, of course. Now, the first electron is being removed from the neutral atom, but the second is being removed from already 1 plus charged ion. So the nuclear charge is attracting that smaller number of electrons more firmly, more strongly. So it's gonna be harder to pull away an electron when it needs that electron. You know, because now you have more protons attracting than the electrons. Or like more protons attracting the electrons they already have. So if you take 1 more, it's gonna be harder to take from an atom that's already unbalancedly charged. Now the second ionization energy of sodium is 9 times larger than the first, while the third is only 1.5 larger than the second. Now to answer this question, we first of all need to write the electronic configuration of sodium. It is 1s2, 2s2, 2p6, and 3s1. Now, what can you see? You only have 1 electron in the 3s shell. So when you take away your first ionization energy, is going to be small because you're taking away this 1 electron. But now your second ionization energy is taking an electron from a fully filled shell. The shell it's taking it away from is full. So now you're going to have to take 1 from a fully filled shell, which is being attracted by the nucleus because it's full. It doesn't want to give anything away. So when you take it away from it, it's going to be way harder to take it away than the first one. That's why it's 9 times greater than the first. That's why second is 9 times greater than the first. In the first, you're taking it away from a shell with only 1 electron. In the second, you're taking it away from a shell that's full, or from like an energy sublevel that's full. But now you're gonna say, okay, why is the third ionization energy only 1.5 times greater? So since, like, let's draw out the 2p6 here. It's 1, 2, 3. What's it called? 1, 2, 3. So I need to add 2. So now we took away 1. We took away 1 in the second time. How are you gonna take another one? Taking another one is gonna be now like you have less, or like you have more electron repulsions, because their spin is like their, what's it called, like now it's easier to take one more. Like now you can take one more, but when you're taking it from a full shell, that's your problem. Now the answer in the mark scheme is what's it called, the first electron is removed from a 3s orbital, while the second and third are removed from a 2p orbital. The 2p orbitals are 1, closer to the nucleus, and 2, they're shielded way less, so they're more strongly attracted to the nucleus. This makes them harder to remove than 3s. But now, when one of the 2p electrons are removed, the remaining electrons are attracted to the nucleus a little more. So the second and third ionization energies don't differ by a large amount. So it's like normal if you're taking from a shell that's already taken away from it. But if you're taking from an already full shell, that's like, it's gonna require much more energy. Now, which of the following graphs represents the first ionization energy variations from left to right across a periodic table? So this is a second take, or like I'm continuing the video because my tablet shut off and it saved the first recording. So now I'm just adding this part on, like, by stitching them together. Anyways, so we were at question 12, part A. Which of the following graphs represents the first ionization energy variation from left to right across period 3? Now we need to know a few things. When you're going across a period, the ionization energy increases. But when you're going down a group, the ionization energy decreases. Now, so by knowing that, we can tell it's A, because it's the only one increasing. Now, how do the ionization energies change down a group, across a period and down the group? Now, in like ionization energy across a period, they increase because there's a higher nuclear charge. Since there's a higher nuclear charge, it will attract the nucleus to the valence electrons more. So you can't like really take electrons that much. So it's gonna like the ionization energy, the energy needed to take these electrons is gonna increase. Whereas when you're going down a group, it's gonna decrease. Why? Because you have extra shielding. When you have extra shielding, the distance between your nucleus and your valence shell is increasing. It's increasing greatly. Since it's increasing, the electrons are less attracted to this nucleus, making the energy required to remove these electrons way less. So when you go down, ionization energy decreases. When you're going across, it increases. Now, periodicity is the recurrence of the same pattern across the rows of the periodic table. This graph shows the ionization energies across period 2. Define the first ionization energy. The first ionization energy is the energy required to remove the most loosely bound electron from each atom in 1 mole of gaseous atoms to form 1 mole of gaseous single positively charged ions. That's the first ionization energy. Now, why is the first ionization energy of lithium less than that of fluorine? So let us first write down the electronic configurations of each. Li is 3, so it's 1s2, 2s1. Fluorine is 9, so it is 1s2, 2s2, 2p5. Now, the lithium and fluorine, they're in the same row. Lithium is here, fluorine is all the way there. So, lithium is less than the first ionization energy of fluorine because lithium has a less nuclear charge. Since it has a less nuclear charge, it will attract its nucleus way less, meaning you will need less energy to take away an electron from lithium. Whereas in fluorine, it has a greater nuclear charge. It's attracting its nucleus more. So you need more energy to pull away that one electron from it. That's why the answer in the mark scheme is the electron is removed from both elements in shell number 2. But the nuclear charge of fluorine is greater, which means that the F nucleus attracts its valence electron stronger than Li, so the ionization energy of fluorine is greater than lithium. Now here it shows you the ionization energies of the successive elements in the periodic table. Now, explain why the ionization energy decreased drastically from B to C. Now, we know that these are the first 20 elements. So this is hydrogen, helium, and whatever. So we know that since B and C, it decreased drastically. How do we know when it decreased? Or why did it decrease? If it decreased, it must mean that they're from different periods, because elements of the same period don't see this much drastic changes. So if it's so if they're from different periods, C must have an extra quantum energy level than B. So its valence electrons are much further from the nucleus, and it will require a lot less energy. And even if you see, this is helium, this is lithium. The lithium is not a noble gas, so also it's gonna be easier to take away from, because noble gases, they don't react with anything, and it's hard to take away anything from them because they're full shells. Now, what can be deduced about B? Let's put them in red. B, E, G, K, and L. Now, we can tell that B, E, and G, since they are peaks, they're the highest points before they drop, they are noble gases. So these three, noble gases. But K and L, they're in the middle. They both have half-filled p orbitals, because how do you know? We know that these are in order, the first 20 ions. So when you see it, it's 1, 2, 3, 4, 5, 6, 7. K is 7. So since K is 7, it is nitrogen. And L is 8, 9, 10, 11, 12, 13, 14. N is 15, which is phosphorus. Nitrogen and phosphorus are in the same period. Or are they in the same group? Wait. Sorry, they're in the same group. Since they're in the same group, they have half-filled p orbitals. They both belong in group 5. To know this information, you need to obviously write down their electronic configuration. Now, question 14. Wait, how many pages do we have left in this chapter? It's not that long, by the way. Yeah, we only have till question 33, and we're in 1 page, 2 page, 3 pages, 4 pages. Yeah, we have 5 pages left. But these questions are really nice, these ones. So explain why the third ionization energy of beryllium is much larger than the third of boron. It's because, listen, when you're looking at them, beryllium is Be, it's in group 2. So it's Be2+. Whereas boron is in group 3, B3+. So the third ionization energy is because, look, here, you can take away 2 electrons from beryllium to make it stable. So after it becomes stable, taking away any more is gonna make it unbalanced. It's gonna make it very much unstable. So after IE2, beryllium becomes stable. So to take an extra electron is gonna be way harder, because after it becomes stable, after it becomes stable, you're taking away from already filled shell that's being attracted by the nucleus. And since it lost already 2, it's closer, it has less energy levels, less shielding. Whereas B3 plus needs to take away 3 to become stable. Now, like here, the 4th ionization energy of boron is gonna probably be something very big. So the 3rd ionization energy of beryllium is the energy needed to remove a 1s. The 3rd ionization of boron is the energy needed to remove a 2s. 2s electrons are further away from the nucleus, and it's less attracted to it, so they require less energy. You could explain it in the way I said it now, or you could explain it in the way of what shells is it being taken away from. Most times, people, you need to always draw down your electronic configuration or keep it in mind, because 90% of the answers, it matters. Now, question 15. Consider the following ionization energies. What element is supposed to have an electronic configuration of He2S1? It is most likely gonna be, so we have 1s2, 2s. He is 1s2, and they want 2s1. Okay, so the 1 is most likely gonna be the one that's gonna increase drastically after the first energy level, so it's most likely X. Because taking away from 2s1 is fine, but taking away from 1s2, it's way closer to the nucleus, so you're gonna require way more energy. So that's why there's a massive jump from IE1 to IE2 in X. Whereas here, it's not that massive of a jump. So it really can't be it, because the nucleus attracts the 1s2 electrons the highest. It's now the answer scheme says for element X, the first large jump is between IE1 and IE2. So it has 1 valence electron, so the configuration is for X. Now the first large jump for IE is Y is between IE2 and IE3, so it has 2 valence electrons. So here you have only 1 valence electron, so it's X. Now why is the first ionization energy of aluminium less than that of magnesium? Now, aluminium is in group 3, magnesium is in group 2. Now listen, for group 2 and 3 and 5 and 6, there is an exception. The ionization energy of group 2 is greater than group 3, and 5 is greater than 6. Even though we said they increase as you go like this, these groups are exceptions. Now, aluminium, let's draw out its electronic configurations. It's Al13, so it's 1s2, 2s2, 2p6, 3s2. Now you have up till now 10, 12, and 3p1. Now, for Mg, it's gonna be 1s2, 2s2, 2p6, and 3s2. So now, when you're removing the 3p1, you can remove it because it's a half-filled shell. It's not even half-filled shell, it's like a 1/6 filled shell. So removing the 3p from the electron from aluminium is easier than removing the 3s from Mg, because 3p electrons are more energetic and it's shielded from the nucleus. But the 3s are more penetrating towards the nucleus, meaning they're more closer to the nucleus. That's why it's easier to take away from aluminium than magnesium. The same applies to group 5 and 6, by the way. Why is oxygen less than nitrogen? It's like I said, nitrogen is in group 5 and oxygen is in group 6. It's for the exact same reason except for different energy levels. So oxygen is 8, nitrogen is 7. So nitrogen is 1s2, 2s2, 2p, it's 2, 4, and 3. Whereas oxygen is element 8, so it's 1s2, 2s2, 2p4. solve this, I need to draw the box, electron in the box configurations. So it's 1s2, 2s2, 2p3. This is aluminium. Now in oxygen, it's the same, but we have one up, 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 down. So here you have 4. So in this orbital, you have more electron-electron repulsions. Here you don't have electron-electron repulsions because they're in different houses. They can't hit each other, you know. Since you have more electron-electron repulsions, it's easier to take away from oxygen than it is nitrogen. And yeah, so the answer in the mark scheme is the first ionization energy of oxygen is less than that of nitrogen, because oxygen's 2p orbital contains 4 electrons where nitrogen has 3. So it has more electron-electron repulsions, making it easier to remove an electron from it. So basically what I said. Now, why is the first ionization energy of sodium less than lithium? Sodium is in group 1, lithium is also in group 1, but their lithium is above sodium. So let's draw their electronic configurations here. Na is going to be 1s2, 2s2, 2p6, 3s1. Lithium is 1s2 and 2s1. Since this is the case, removing a 3s electron is way easier than removing a 2s electron, because 3s electrons are more shielded. Since they are more shielded, it's gonna require way more energy. It's gonna require less energy since they're more shielded. Like you have 1s, then 2s, then 2p, then 3s. Whereas here you have 1s and 2s. And here's the nucleus. So to remove one from here is easier than to remove one from here, because this is way more heavily guarded by the nucleus. That's why the first ionization energy of sodium is less than that of lithium. And why is the first ionization energy of sodium less than that of magnesium? So sodium is like this electronic configuration, magnesium is the same +1, like it's just 3s2. So for they have, both of them are in the same period. So they have the same shielding, but Mg has a greater nuclear charge. So the nucleus for Mg attracts the valence electrons more. So you need greater ionization energy to remove them. Now, explain why the first ionization energy of indium is much lower than cadmium, even though the nuclear charge of indium is greater than that of cadmium. Now, we first need to find out where they are. Indium is in group 3, where cadmium is before it in the periodic table, but it's in a transition metal. So we should write down both of their ionization energy. We should write down both of their, what's it called, electronic configurations. Since they have very big electronic configurations, I'm not gonna write it all. We're gonna write shorthand. So they're both, one of them is krypton. This is for question 20, by the way. I don't know why I'm writing it here, but there's no space. 4d10, 5s2, and 5p1. And for krypton, for cadmium, this is for In and this is for CD. It's krypton, 4d10 and 5s2. So we said that the question is asking us why is it more to take from cadmium, or sorry, why is it lower? No, why is indium less than taking from cadmium? It needs less energy than taking from cadmium, even though indium is to the right of it on the periodic table. Now, always, first thing you need to do is write down electronic configuration. As you can see, indium taking away from 5p1 is easier than taking away from 5s2, because 5p1 is more shielded than 5s2, so it is easier to take it away from it. And yeah, removal of 5p electrons requires less energy than 5s, since it's more shielded, basically. This question, I doubt it's coming, it's not even grid. This is for question 20. Now, question 21 is saying these are the ionization energies of element Y in the given head. Write down the formula of element Y with magnesium. Now we know magnesium is Mg, 2 plus. Let's find out what y is. Now to find out the easiest way, now you could do it two ways. You could either find out the ratios between IE2 and IE1, IE3 and IE2, IE4, and you get the idea. Or you bad guys again, because my tablet cover, whenever it touches in a way, it closes my tablet, and when my tablet closes, it just saves the recording. It doesn't let me continue it. So I was saying that you first need to find where's the first big jump. As you could see, IE1 to IE2 is normal, this is normal, this is normal, this is normal, but then from 3,000 to 15,000 is very big jump. Since it's a very big jump, what's it called, between IE5 and IE6. So we know that IE5 till here, this must be valence electrons, because if you're taking away from a valence electrons, it isn't supposed to have that much charge. But if you're taking away from the core electrons, it's gonna have a big jump. So if it's fine till IE5, it means it has 5 valence electrons, making it in group 5. Anything in group 5 is, we're gonna call it Y3 plus, or is it Y3 plus, or no, sorry, Y3 minus, because it's group 5. So now we need to do the crisscross method. It's Mg3 Y2, and that's the element. Now, almost done. Define electron affinity and write down an equation to represent the first electron affinity of oxygen. Electron affinity is the energy needed to add an electron of a gaseous atom, and the equation is going to be O in a gaseous form plus 1 electron is O minus in a gaseous form. It's not O2, because they got that question in the AMS where they asked us of it was chlorine. Now the first electronic affinity of oxygen is exothermic, while the second is endothermic. Now it's because adding an electron to a negative ion leads to the repulsion, so you need energy to overcome this repulsion. But in the second, you don't need that energy. There's no electron repulsions to repel it. Now question B is asking, why is the electron affinity of fluorine less than that of chlorine? Now F is above Cl in the periodic table, and we should memorize that as you go from left to right on a period on the periodic table, the electron affinity is more negative, so it's more exothermic. So and when you're going down, it's less negative, so it's more endothermic. So the smaller energy release is because of the small size of the 2p orbitals in the F atom. The smaller the orbital size means that the 2p are very close together, so they have larger electron repulsions, so they'll be repelled more strongly, and the energy needed to overcome the repulsion is greater. So the addition of an electron to F is a smaller release of energy compared to chlorine, because you need more energy to overcome the repulsion, because they're less shielded. Fluorine is less shielded. Now you're gonna say, but this is going against what I said. Know one thing. Okay, so I'm gonna draw it out, and know that this part is an exception to the rule. 23 part B is an exception to the rule. It's because as we go like this, it is the EA is more negative, and when you go down, it is less negative. So this is an exception to the rule because it's going against what I just said within this periodic table. So yeah, it's supposed to be the electron affinity of fluorine is supposed to be greater than the one of chlorine, but it's an exception, so it's not. Now here we're talking about the bonds between these types of structures. Lithium is a metal, so it has a metallic bond. I'm gonna write M for metallic. Beryllium, also a metal, so M. Carbon, it is in group 4. So anything in group 4 is a giant molecular structure. And anything after that is simple molecular structure, simple molecular structure, simple molecular structure. Okay? So now next question. The period 2 exhibits different trends in their physical properties across the period. The graph shows the variation in the melting points as we go from left to right. Now it's asking us to explain the difference in the melting points between lithium and beryllium. Lithium is the strength of the metallic bond it increases when the nuclear charge increases and the number of valence electrons increases. So lithium forms a +1, which contributes to pulling in more in the sea of the delocalized electrons, whereas beryllium is 2+, so it contributes 2 valence electrons to the sea of the delocalized electrons, which means it has a higher melting point. Now explain the trend from nitrogen to neon. Nitrogen, oxygen, and fluorine are all gaseous and diatomic, and neon is gaseous and monoatomic. And all of these have very low boiling points due to their intermolecular forces being very weak. Now, explain the high melting point of carbon. Carbon is held together by, we just said above, it's a strong molecular covalent structure. And the bonds between them are covalent bonds. Between the molecules of carbon is strong covalent bonds. They're very, very hard to break. That's why it has a high melting point, because you need a lot of energy to break them. Now, what are the factors that influence the electronegativity value of elements? There's 3 factors, and the 3 factors that affect electronegativity are nuclear charge, shielding, and atomic radius. So memorize that. It is nuclear charge, shielding, and atomic radius, which I name AR. Electronegativity increases across a period from group 1 to 17 and decreases down a group. It's giving you a piece of information. Which of the following is responsible for the above trends in electronegativity? So why? Now, when we go across a period, the nuclear charge increases. Yes, when nuclear charge increases, we have more electronegativity. As we move across a period, the atomic radius decreases. Yes, because we said higher nuclear charge, so it's gonna pull in its electrons more. That's why it's more electronegative. That's another reason. As we move down a group, the shielding effect increases. Yes, because down a group you have more energy levels shielding it. Now, as we move down a group, the nuclear charge decreases. No, this isn't true. Nuclear charge when we move down a group increases greatly, actually. So this is wrong. As we move down a group, the atomic radius increases. Yes, it does, because you have more energy levels, so it's gonna increase, of course. Now, 3 questions left, supposedly. No, 33. Oh, never mind. I thought there's 31 questions. Arrange the following elements in increasing order of electronegativity. So you need to, for this question, you have to look at your periodic table. But know that metals are gonna most likely be to the left of the electronegativity spectrum. Now, Na is first because Na is under lithium. Na is under lithium, so it's what's it called? Its electronegativity is the least. So it's Na, lithium is greater than Cl is less than fluorine. Because it's when you go up a group, it increases, but when you go down, it decreases. So it's Cl then fluorine. And take it as a note, fluorine is the most electronegative. What's it called? It's the most electronegative out of all the elements on the periodic table. And again, I said this yesterday in my video, but please read the book, because this time it's very important, because the only thing we have to study is the book, these CQDs that I'm explaining, and there's no course practice. So if you want for extra practice on the written, you need to study past paper questions from AP exams or from your AP classroom. Now here, same thing, K, then Ca, because K is to the left of Ca on the periodic table, then As, then it is K, it's N, because N is way more electronegative than As. Now write the electronic configuration of gallium. I don't know why we're doing this. So gallium is 31, and the next, okay, so it's argon, 3d10, and then 4s2. Wait, is gallium, yeah, it's 31. Anyways, and then 4p1. So the electric conductivity changes across a period according to the type of structure. Complete the graph to show you how it changes. So we're gonna know that it's increasing from Mg to Al, and then it drops suddenly from Si and flatlines here. It's dropped here, by the way, it's just my pen. And flatlines. That's it. That's all you need to know. Gallium is the same group as aluminium. Okay. Write the chemical reaction between gallium and oxygen gas. So aluminium is Al3+, so it's gonna be Ga plus O2, later I balance, gives you Ga2O3, Ga2O3, and now we balance. So since you have here 2 Ga and now you have 3, so here we have to multiply by 2. So it's, I think the mark scheme, by the way, is very wrong for this. Since it's Ga2, here it needs to be 4 Ga. In the mark scheme it says it's 2 Ga. And O2, of course, it has to be 3. Wait, no, something's wrong. In the mark scheme, I'm very sure it's wrong, because it needs to be here 3, therefore, because look, 2 Ga, 2 is 4, and here you have 4 Ga, 3 times 2 is 6, and here you have 2 times 3 is 6. So I'm gonna check with my teacher why it's written like that in the mark scheme, and I'll update later on it. Write the reaction between gallium and chlorine gas. So it's gallium, Ga, plus Cl2, giving us what's it called, GaCl3. Now again, we need to multiply by 2 here and 3 there to balance it out. And you need to multiply gallium by 2. This one is correct in the mark scheme. Write the chemical equation that occurs between potassium and water. Potassium and water, so it's gonna be 2K plus 2H2O gives you 2KOH. I can't really teach you how to write chemical equations because we've been taking it for years, and I'm assuming a lot of people know how to do it by now. And now, which of the elements would react more vigorously with oxygen gas, lithium or boron? Lithium is gonna react more vigorously because lithium has a smaller ionization energy, so it's more ready to react. And anytime you see group 1 elements are very, very, very highly reactive, they will react with anything much faster or more vigorously. Now 32, complete the table. The oxide is Na2O because O is 2- and Na is Na+. and it's NaCl. Mg is 2 plus and O is 2 minus, so they balance out, MgO. And Mg is 2 plus and Cl is Cl minus, so it's Cl2. You do the crisscross method from last year. Al is 3 plus and O is 2, so it's Al2O3. And here it is AlCl3. Si is Si4 plus and O2 minus, so it's supposed to be Si2O4, but you can take the simplest one, so it's SiO2. And here it's SiCl4. Now phosphorus is an exception. Memorize it. It's phosphorus P4O10 or P2O5 and PCl5. They bring this in the exam also. And yeah. Now manganese and calcium metals react vigorously with acids upon strong heating. Calcium metal gives a bright red brick flame, while magnesium burns with a bright white flame. Write the electronic configuration of Ca2. I'm gonna write shorthand because I think we all know how to write by now. It's Ne, 3s2, 3p6. Okay? That's the Ca2 plus. Now consider, sorry guys, my mic lagged. Anyways, consider the data given and explain why the first ionization energy of magnesium is larger than that of calcium. So they told you that the first ionization of magnesium is 738, second is 1451, and 590 and 1145. So magnesium is obviously larger than that of calcium, the ionization energy. You could even calculate the ratio. Now, the valence electrons in calcium are 4s2, whereas in magnesium, the valence electrons are 3s2. 4s2 are more shielded than 3s2. They're less attracted to the nucleus, so they're easier to remove. That's why. So now, one theory to explain the color observed when heating, one theory, is that the brick red color corresponds to the photons that have enough energy to ionize the Ca atoms into Ca2 plus atoms. We've never actually taken this, but it's relatively easy to do. We know that the formula is what's it called? Hc over lambda equals energy. So here we're we're trying to look for the energy. So the energy is gonna be H, which is 6.626 because it's Planck's constant, times 10 power negative 34. I doubt they're gonna get us questions like this, by the way. Times 2.99 or 998 times 10 power 8 all over the wavelength of the red light, which is given here, which is 634 nanometers. So 634 times 10 power negative 9. And then you need to find, you find the energy, which is equal to 3.13 times 10 power negative 19. And is his theory justified? Now, is his theory justified? To know this, we need to see what's the energy needed to, what's the energy needed per photon. First of all, we need to add these two numbers together. So we have 738, or wait, we're talking about calcium. These two numbers then. 590 plus 1145, which gives us 1735. So far, easy. Now, this is kilojoules per mole. We need it per photon. To make it per photon, you divide it by Avogadro's number. So it is times 10 power 3, because this is in kilojoules. So you need to make it in joules. Per mole, which is 6.022 times 10 power 23. So then it's gonna equal to 2.88 times 10 power negative 18. So this number is bigger than this number. So the energy required to ionize is more than what is proven to be the photon of brick red light. So his theory is unjustified. And that is it for this video. Hope you understood everything. Very sorry for my tablet closing 3 times and the mic error I had in the middle. Hope you understood everything. Have a great day. Bye.